Tonight, we are going to place our galaxy inside the universe and ask a question that seems simple until the first distances begin to unfold. How big is the universe compared with the Milky Way? Our galaxy is already so large that light, the fastest messenger permitted by modern physics, needs roughly 100,000 years to cross its bright stellar disk. A pulse leaving one side when early human populations were spreading through unfamiliar landscapes would only now be reaching the other. That is only one galaxy. The observable universe is roughly 93 billion light-years across in present distance terms. Along one straight line, nearly 1 million Milky Way disks could fit from one side of that observable region to the other. And even that comparison hides most of the difference. A diameter measures only one direction. Space extends in three. When we compare volumes rather than widths, the contrast rises from nearly 1 million to hundreds of quadrillions of idealized Milky Way-sized regions. Yet none of those numbers describes the confirmed size of the entire universe. They describe only the part from which information has had time to reach us. Beyond the observable horizon, the universe may continue much farther. It may be finite, but vastly larger than the region we can measure. It may also extend without any known end. By the end of tonight, you're going to understand how the size of the observable universe compares with our galaxy, why that comparison is more complicated than dividing one diameter by another, and why the full universe may be far larger than anything we can currently measure. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To make the comparison meaningful, we first need to understand our position. Earth is not floating outside the Milky Way with a complete spiral galaxy hanging in the distance. We are embedded within it. Our planet orbits the Sun at an average distance of about 150 million kilometers. Light covers that distance in a little more than 8 minutes. The Sun is one star among hundreds of billions in the Milky Way. It lies roughly 26,000 light-years from the galactic center, inside a smaller structure commonly called the Orion Spur. From Earth, the Milky Way appears as a pale band crossing a dark sky. That band is not a nearby cloud. It is the combined glow of distant stars seen through the crowded plane of the galactic disk. We are looking through the galaxy from within. Toward the center, our view passes through dense star fields, dust, gas, and ancient stellar populations. Away from the galactic plane, the sky appears less crowded because our line of sight leaves the thin disk more quickly. This creates a difficult observational position. It is like trying to understand an enormous forest while standing between the trees. We cannot travel far enough above the Milky Way to photograph its complete shape. Instead, astronomers reconstruct it through measurements of stars, gas clouds, infrared light, radio emission, stellar motion, and gravity. The result is a barred spiral galaxy. At its center lies a dense bulge of old stars and a supermassive black hole known as Sagittarius A star. Extending outward is a flattened disk containing spiral structure, star-forming regions, dust, gas, and most of the bright stars we associate with the galaxy. Beyond that disk is a much fainter halo. It contains scattered stars, ancient globular clusters, streams left by disrupted dwarf galaxies, hot gas, and a much larger distribution of dark matter. This means the Milky Way has no single obvious edge. If we mean the bright stellar disk, a useful width is about 100,000 light-years. The stars do not stop at a clean boundary, but the estimate gives us a practical ruler. If we include the faint stellar halo, the galaxy extends farther. If we include its surrounding gas and dark matter, its gravitational territory may reach hundreds of thousands of light-years from the center. For tonight's main comparison, we will use the familiar 100,000 light-year disk. That distance is already difficult to feel. Light can circle Earth more than 7 times in 1 second. It reaches the Moon in about 1.3 seconds. It travels from the Sun to Neptune in several hours. but it needs roughly 100,000 years to cross the Milky Way. A spacecraft would need vastly longer. Voyager 1 is leaving the solar system at around 17 kilometers per second. That is extraordinary by human engineering standards. Yet at a similar speed, crossing the Milky Way would require billions of years. Even the galaxy itself would change during the voyage. Stars would move along their orbits, gas clouds would collapse, new stars would ignite, massive stars would die, dwarf galaxies would be stretched and absorbed. The traveller would not arrive in the same Milky Way it had entered. Our Sun completes one orbit around the galactic centre in roughly 230 million years. Since the Sun formed, it has travelled around the galaxy only about 20 times. Recorded human history occupies such a tiny fraction of one galactic orbit that it would almost disappear on the scale of the journey. This is the object we are about to compare with the universe. The Milky Way is not small. It contains nearly every star visible to the unaided eye. It contains planetary systems, nebulae, stellar remnants, magnetic fields, radiation, gas, dust, and invisible matter. Every spacecraft ever built remains extremely close to the Sun when measured against the galaxy's full width. Voyager has travelled farther than any other human-made object, yet it has crossed only a microscopic fraction of 1 light-year. The distance across the solar system is almost nothing compared with the distance between stars. The distance between stars is almost nothing compared with the width of the Milky Way. And the width of the Milky Way will soon become our smallest useful cosmic ruler. Before we leave it behind, however, we need to understand what the galaxy includes. The bright spiral is only the visible centre of a much larger gravitational environment. Its true boundary fades through stars, gas, satellite galaxies, and dark matter. The Milky Way does not end like a wall. It dissolves into the space around it. The familiar spiral is the part of the Milky Way that shines strongly enough to dominate our imagination. Most illustrations show a bright central region, curved arms, and a clean edge against black space. The picture is useful, but it quietly suggests that the galaxy is a solid object with a definite surface. Real galaxies are not built that way. Their boundaries depend on what we decide to measure. If we count bright stars, the Milky Way appears to thin beyond its main disk. If we follow faint stars, ancient clusters, and stellar streams, it extends farther. If we trace hot gas, the galactic environment becomes larger again. If we follow gravity, the boundary expands into an enormous dark matter halo that cannot be photographed directly. At the centre of the Milky Way is the galactic bulge. It contains a dense mixture of stars, many older than the Sun. Passing through the bulge is a long central bar formed by stars moving on organised orbits. Near the middle lies Sagittarius A star, a black hole with a mass roughly 4 million times that of the Sun. That sounds overwhelming, until we compare it with the galaxy around it. The Milky Way contains hundreds of billions of stars. Their combined mass is far greater than that of the central black hole. The stars of the galaxy do not all orbit Sagittarius A star in the simple way planets orbit the Sun. They move within the combined gravitational field of stars, gas, dark matter, and every other mass contributing to the system. A galaxy is not merely a collection of suns circling one central object. It is a self-gravitating environment made from visible and invisible components. The disk is the most recognizable part. Its width is roughly 100,000 light-years, although estimates vary because the outer stellar population fades gradually rather than stopping at one exact distance. Its thickness is far smaller than its width. The thin disk, where much current star formation occurs, is only around 1,000 light-years thick in many regions. This creates the flattened form associated with spiral galaxies. Inside that disk, stars and gas follow broad spiral patterns. The arms are not rigid structures containing the same stars forever. They are regions where matter becomes temporarily more concentrated. Gas clouds entering denser areas may be compressed under suitable conditions, Parts of those clouds collapse and form stars. Bright young stars illuminate surrounding gas, making some spiral regions stand out. But most stars move through changing patterns rather than remaining permanently fixed inside one arm. The Sun is doing this now. It travels around the galactic center at hundreds of kilometers per second, carrying Earth and the other planets with it. The motion feels still because nearby stars share broadly similar paths. The disk also contains cosmic dust. This is not simply dirt scattered through space. It consists of tiny grains formed from materials such as carbon compounds and silicates, often produced or recycled through earlier generations of stars. Dust absorbs and scatters visible light. It is one reason we cannot look directly through the Milky Way's plane and see its entire structure. Toward the center, broad clouds hide many stars at visible wavelengths. Astronomers therefore study the galaxy in many forms of light. Infrared observations reveal regions partly hidden by dust. Radio measurements trace cold hydrogen and molecular clouds. X-rays expose hot gas and energetic events. Precise stellar motions help reconstruct invisible mass. The Milky Way becomes a layered model, assembled from different kinds of evidence. Outside the thin disk lies a thicker population of stars. The thick disk reaches farther above and below the galactic plane. Its stars are generally older and often preserve different chemical histories. Those histories are written in starlight. The earliest generations formed when the universe contained mostly hydrogen and helium. Later stars formed from material enriched by previous stellar lives. Carbon, oxygen, iron, and many other elements were produced inside stars or during their deaths, then returned to space. The Sun and Earth formed from this recycled material. The galaxy is therefore not only a structure in space, it is a record of chemical inheritance. Beyond the disk lies the stellar halo. It is more spherical than the flattened disk, though its true form is irregular. Its stars are extremely sparse. An observer passing through it would not see a glowing shell around the Milky Way. Most of the region would remain dark. Within the halo are globular clusters, dense, spherical collections containing thousands or millions of old stars. There are also long stellar streams. Some are the remains of smaller galaxies and clusters pulled apart by the Milky Way's gravity. Their stars have been stretched along orbital paths, leaving faint evidence of earlier encounters. The galaxy grew partly by absorbing smaller systems. That process is still continuing. Surrounding the stars is a vast region of thin, hot gas called the circumgalactic medium. It forms an extended atmosphere between the visible galaxy and intergalactic space. The gas is difficult to detect because its density is extremely low. Astronomers often identify it through its effects on light from more distant objects. This medium is not an inactive border. Material can be driven outward from the disk by stellar explosions and energetic activity. Some may later cool and return. Gas from beyond the galaxy can enter the halo and eventually contribute to future star formation. The Milky Way exchanges matter with its surroundings over millions and billions of years. And still, the largest component remains hidden. The motion of stars and satellite galaxies shows that visible matter cannot explain the full gravitational field. Far from the center, stars move faster than expected if nearly all the mass were concentrated in the bright disk. The leading explanation is dark matter. Dark matter does not emit, absorb, or reflect ordinary light in a way telescopes can photograph directly. Its presence is inferred through gravity. Around the Milky Way, it appears to form a vast halo extending far beyond the visible stars. Its exact boundary is uncertain. Dark matter density decreases gradually, and the Milky Way's halo interacts with the wider gravitational environment of the local group. Depending on the definition, the halo may extend hundreds of thousands of light-years from the galactic center. The full gravitational system could approach 1 million light-years across. That larger figure changes the size ratio, but it does not change the central conclusion. Even an extended Milky Way halo remains tiny beside the observable universe. For consistency, our main ruler will remain the bright disk. 100,000 light-years. It is clear enough to picture and stable enough for a meaningful comparison. But every time we use it, we should remember what lies outside. The visible spiral is not the whole galaxy. The Milky Way continues through faint stars, hot gas, dark matter, and gravitational influence. Its edge is not a line. It is a fading relationship. And once that relationship weakens, the galaxy becomes one member of a larger family, rather than the environment filling every direction. The phrase 100,000 light-years is accurate, but accuracy alone does not create intuition. The number is too far beyond ordinary experience. We hear it, understand that it is large, and continue without feeling the journey hidden inside it. A light-year is the distance light travels through a vacuum in 1 year. That distance is about 9.46 trillion kilometers. It is a measure of distance, despite the word year. Light travels at nearly 300,000 kilometers per second. At that speed, it reaches the moon in a little more than 1 second. It crosses the average distance between the Sun and Earth in about 8 minutes and 20 seconds. It reaches the outer planets after several hours. Then the emptiness between stars begins. The nearest star system beyond the Sun, Alpha Centauri, lies more than 4 light-years away. Light leaving Earth tonight would not arrive there for more than 4 years. That is only the first small interval in the galaxy. To cross the bright disk of the Milky Way, the same light must continue for roughly 100,000 years. This gives us a useful ladder. The solar system is measured in light hours. The distances between nearby stars are measured in light years. The Milky Way is measured in tens of thousands of light years. Each step changes the kind of journey we are imagining. Suppose a pulse of light begins near one edge of the galactic disk. At first, it passes through a local neighborhood of stars. Those stars are not packed together like points inside a glowing cloud. Even in the disk, space is overwhelmingly empty. Near the Sun, typical stellar separations are several light years. If the Sun were reduced to the size of a grain of sand, nearby stars would still be separated by kilometers in a similar model. The galaxy contains hundreds of billions of stars, not because they are crowded closely together, but because the volume of the disk is immense. After 1,000 years, our pulse would have crossed a distance greater than anything humans have physically explored. Yet it would have completed only about 1% of the Milky Way's width. After 10,000 years, civilizations could rise, transform, and vanish while the light remained. Well inside the galaxy, after tens of thousands of years, it might pass through the broad central regions, depending on where the journey began. The center would not appear as one bright lamp. It is a complicated environment filled with dense star fields, gas clouds, stellar remnants, radiation, magnetic activity, and the gravitational influence of Sagittarius A star. Dust would hide many regions from visible light. Infrared and radio radiation would reveal structures unavailable to human eyes. Then the pulse would continue outward through the opposite half of the disk. By the time it reached the far side, roughly 100,000 years would have passed. During that interval, stars would have shifted along their orbits. Some massive stars would have formed and died. Gas clouds would have collapsed into new systems. Others would have been scattered by radiation and shockwaves. The galaxy crossed at the end would not be identical to the galaxy entered at the beginning. On human timescales, the Milky Way appears almost permanent. On light-crossing timescales, it is alive. This creates a strange consequence whenever we observe distant parts of our own galaxy. We do not see them as they are at this moment. We see them as they were when their light began traveling toward us. A star 10,000 light-years away appears through light that started its journey 10,000 years ago. A region on the far side of the disk may be visible tens of thousands of years in the past. There is no single visual present of the entire Milky Way available from Earth. Every direction contains a different layer of galactic history. The galaxy is not only wide in space, it is deep in time. Now replace light with a spacecraft. Voyager 1 travels at roughly 17 kilometers per second relative to the Sun. At that speed, reaching even the nearest star would require tens of thousands of years if the probe were traveling toward it. Crossing the Milky Way would require billions of years. The exact duration would depend on the path and changing motion, but the central point remains. A spacecraft moving at current speeds would need a period comparable to a major fraction of cosmic history. The vehicle would face more than distance. Its energy systems would fail, materials would degrade, navigation targets would move, tiny particles would become dangerous at higher speeds. The galaxy's gravitational environment would change during the voyage. A galactic crossing cannot be treated like a longer ocean journey. The vehicle, destination, and surrounding galaxy would all evolve. Suppose a future craft could travel at 1% of light speed. That would be about 3,000 kilometers per second, far beyond the sustained speed of any existing spacecraft. Even then, crossing 100,000 light-years would take roughly 10 million years in the galactic frame. At 10% of light speed, the journey would still last about 1 million years. At half the speed of light, ignoring the immense energy and engineering problems, the crossing would require roughly 200,000 years for observers remaining with the galaxy. Relativity could reduce the time experienced by travelers moving extremely close to light speed. But it would not make the galaxy small. The energy needed to accelerate a massive craft would rise dramatically. Impacts with tiny dust grains could become catastrophic. Shielding would become a central problem. The speed of light is therefore more than a convenient ruler. It is a boundary shaping communication, travel, and causality. No signal can move instantly from one side of the Milky Way to the other. A message requires tens of thousands of years to cross the disk. A reply requires tens of thousands more. Two civilizations on opposite sides of the galaxy might detect one another and still never hold anything resembling a conversation. By the time a response arrived, languages, technologies, cultures, and perhaps biological forms could have changed beyond recognition. The Milky Way is large enough to break the ordinary meaning of connection. It can be one gravitational system without becoming one immediate community. Its parts share motion and history, yet remain separated by time. And still, when we move beyond the galaxy, this enormous width becomes only a starting unit. If the Milky Way were reduced to a coin, the nearest major galaxy would not touch it. Andromeda would be another coin placed about 25 coin widths away. Beyond that pair would lie smaller galaxies, wider groups, richer clusters, long filaments, and voids so large that the coin-sized Milky Way would become almost impossible to notice. We have crossed a galaxy that light needs 100,000 years to traverse. Now we are ready to leave it behind. The first surprise is how quickly something this enormous becomes a single object in the dark. From far enough away, the Milky Way's hundreds of billions of stars blend into one structure. The individual suns disappear first. Then smaller star-forming regions lose their detail. The spiral arms become soft bands. The central bar contracts into a brighter concentration. The faint halo vanishes into the surrounding darkness. Eventually, the entire galaxy becomes one luminous mark. Nothing about the Milky Way has physically changed. Only our viewpoint has changed. This is one of the central lessons of scale. An object can remain unimaginably large while becoming visually insignificant inside a larger environment. Imagine moving away from Earth at the speed of light. After a little more than 1 second, the Moon's distance lies behind us. After 8 minutes, we have travelled about as far as the separation between Earth and the Sun. Several hours later, we are beyond the major planets. But the solar system has no simple edge. Beyond Neptune lie icy objects, scattered populations, and the distant gravitational influence of the Sun. Depending on the boundary we choose, leaving the full solar environment could require much longer. Even then, the Milky Way would appear almost unchanged. We would still be surrounded by nearby stars. The constellations would slowly distort as our position changed, but the galaxy would remain the world containing every direction. After 1 light year, we would still be closer to the Sun than to another stellar system. After more than 4 years, we could reach the region of Alpha Centauri. On a galactic map, the Sun and Alpha Centauri would appear almost on top of each other. To gain a true external view of the Milky Way, we would need to travel much farther. Thousands of light years above the disk, broad patterns might begin to appear. Dust would still hide some regions, and the perspective would remain too close for a complete portrait. At tens of thousands of light years, the disk would start fitting into a wider field of view. At a distance comparable to its own width, the Milky Way would finally appear as a large but contained object. Imagine a coin representing the bright disk. From 1 coin width away, it still dominates the view. From 10 coin widths, it becomes a smaller part of the scene. From 100 coin widths, most internal detail begins to vanish. The coin remains unchanged. The darkness around it increases. As we travel outward, we pass through the Milky Way's halo. The density of stars drops dramatically. Globular clusters and stellar streams remain scattered through the region, but the disk recedes behind us. We move through hot diffuse gas and the invisible dark matter halo. There is no moment when a sign announces that we have left the galaxy. Its gravitational influence simply weakens. The influence of satellite galaxies and the wider local group becomes more important. The Milky Way has many known companions. The large and small Magellanic Clouds are among the most familiar from parts of Earth's southern hemisphere. They appear as faint patches of light. They are not atmospheric clouds. They are nearby dwarf galaxies with their own stars, gas, and histories. Other satellites are much fainter. Some contain so few stars that they are difficult to distinguish from the foreground population of the Milky Way. Their total mass may be dominated by dark matter. Several are being distorted or stripped by our galaxy. Viewed from outside, these companions reveal that the Milky Way is not isolated, even in its immediate surroundings. Some satellites orbit within its extended halo. Some are falling inward. Some have passed through regions of the galactic environment. Some may eventually lose their separate identities and contribute stars to the Milky Way. This is one of the ways large galaxies grow. A galactic merger is not normally a collision between solid walls of stars. The distances between stars are so great that direct stellar impacts remain rare. Gravity acts across the entire system. It changes orbits, stretches structures, compresses gas, and redistributes matter over immense periods. Evidence can remain long after a smaller galaxy has been disrupted. Faint streams around the Milky Way are records of earlier encounters. They show that the galaxy assembled through a long sequence of additions rather than appearing in its current form all at once. From a distance, the Milky Way would not look perfectly symmetrical. Its disk is warped. Its halo is uneven. Its surroundings contain debris, companions, and signs of ongoing interaction. The clean spiral seen in illustrations is a useful summary, not a complete portrait. Continue outward. At hundreds of thousands of light years, the bright disk shrinks into a compact oval. At 1 million light years, the Milky Way is no longer the environment around us. It is an object behind us. That distance is roughly 10 times the width of its bright disk. Yet we have still not crossed the larger family to which the galaxy belongs. This is where the role of our measuring stick changes. Inside the Milky Way, 100,000 light-years defines an almost impossible crossing. Outside it, the same distance becomes a modest interval between larger structures. A light-year that seemed immense within the solar system became ordinary between stars. 1,000 light-years that seemed vast among nearby stars became only part of the galactic disk. Now the entire width of the Milky Way becomes a useful unit for intergalactic space. Andromeda, the nearest large spiral galaxy, lies about 2.5 million light-years away. That is roughly 25 Milky Way disk widths. If the Milky Way were a dinner plate, Andromeda would be another plate several meters away. Between them would be mostly darkness, thin gas, dwarf galaxies, and matter too faint to see directly. Photographs often hide this emptiness. Galaxies are framed closely to make their structures visible. The intervening space is reduced or cropped away. In reality, a group of galaxies is dominated by the distances between its members. The galaxies are bright landmarks. The darkness is the territory. A signal transmitted from the Milky Way tonight would require about 2.5 million years to reach Andromeda. A reply sent immediately would return around 5 million years after the original message began. When the message left, no member of our genus existed. When the answer returned, the civilization that sent it might be unrecognizable or gone. Intergalactic distance turns conversation into evolution. The Milky Way, which once surrounded every direction, has become one luminous island among others. And those islands reveal that we have entered a structure far larger than any single galaxy. We have entered the local group. The local group is the first clear demonstration that galaxies do not simply drift at random. They gather under gravity. Some orbit larger systems. Others follow long paths shaped by the combined mass of the entire region. Over billions of years, smaller galaxies can be stripped, distorted, or absorbed. The local group contains the Milky Way, Andromeda, the Triangulum galaxy, and many smaller members. The exact number changes as astronomers discover faint dwarf galaxies and reconsider whether distant candidates are truly bound to the group. But the broad structure is clear. Two large spirals dominate. The Milky Way is one. Andromeda is the other. Triangulum is smaller than either, though still a substantial spiral galaxy. Around them are dwarf systems ranging from relatively bright companions to extremely faint collections of stars. The local group spans roughly 10 million light-years, depending on the boundary used. That makes it around 100 times wider than the bright disk of the Milky Way. If our galaxy were reduced to a coin, the local group would fill something closer to the width of a room. The Milky Way and Andromeda would be the largest coins, Triangulum would be smaller, the dwarf galaxies would become tiny marks scattered through the surrounding space. Most of the room would still be empty. The local group is not a crowded city. It is a wide gravitational territory containing a few major concentrations. This is where a natural intuition begins to fail. Stars gather into galaxies, so we may imagine that galaxies gather into something resembling an even larger galaxy. Perhaps one central system sits in the middle, while the rest orbit in a clean disk or sphere. The local group is not organized that way. It has no single glowing center equivalent to the center of the Milky Way. It has no spiral arms made from galaxies. Its members do not move in one simple pattern. It is a loose association, still evolving. The Milky Way and Andromeda are approaching one another in radial motion, but their long-term future is not as certain as older descriptions suggested. For many years, a collision and merger several billion years from now was often presented as nearly inevitable. More recent analyses combining improved motion measurements and the gravitational influence of other local group members have made that outcome less certain. Current modelling suggests something closer to an even chance of a Milky Way-Andromeda collision within the next 10 billion years. The exact probability depends on small uncertainties in sideways motion, and on the influence of galaxies such as Triangulum and the Large Magellanic Cloud. This updated picture is more interesting than a guaranteed merger. It shows how tiny changes in motion can reshape a future unfolding across millions of light-years and billions of years. The local group is predictable in broad gravitational terms, but not in every detail. If the Milky Way and Andromeda pass close enough, their gravity would reshape both systems. Their disks could stretch and distort, gas might be compressed, Stellar orbits would change. Direct collisions between individual stars would remain unlikely because the spaces between them are immense. If they miss a close encounter, they could remain separate for much longer or follow another sequence of interactions. The future is a range of possibilities, not a completed diagram. This matters because the local group introduces a central distinction. Some structures are gravitationally bound. Others are not. Within the Milky Way, gravity clearly dominates over cosmic expansion. Within the local group, gravity is also strong enough to maintain a shared environment. The space between the Milky Way and Andromeda does not simply expand according to the average cosmic rate, as though the galaxies were passive markers. Their mutual gravity and the mass of the group shape their motion. Beyond the group, however, expansion becomes increasingly important. Distant galaxy groups can recede from one another as the space between them grows. This expansion does not stretch the Milky Way. It does not pull apart the solar system. It does not enlarge atoms or the human body. Local forces are far stronger on those scales. Gravity binds galaxies and planetary systems. Electromagnetic forces bind matter. Cosmic expansion becomes important across the enormous spaces between large structures that are not gravitationally connected strongly enough to resist it. The local group therefore marks a transition. Inside it, gravity can preserve a common future. Beyond it, many structures are participating in the larger expansion of the universe. The boundary is not a wall. Astronomers estimate membership by studying distance, velocity, and gravitational influence. Near the edge, the classification becomes less clear. Some galaxies may be passing near the local group without remaining bound. Others may be entering its environment. Some may lie in nearby associations, responding to different concentrations of mass. The local group is embedded within a broader cosmic neighborhood. The nearest large galaxy cluster is the Virgo cluster, tens of millions of light years away. It contains far more galaxies than our group. For many years, the Milky Way was described as part of the Virgo supercluster, because the local group lies within a wider concentration connected with Virgo. Later studies of galaxy motions described a broader region called Laniakea. The name refers to an immense heaven. It captures the scale, but it should not imply one stable object with a sharp boundary. A supercluster is not necessarily bound together forever. Some parts may move toward dense regions, others may be carried apart by cosmic expansion. The term can describe a pattern in the distribution and flow of galaxies without meaning that every member will eventually collapse into one system. This is another failure of repeated architecture. A galaxy is not a larger solar system. A galaxy group is not a larger galaxy. A supercluster is not simply a larger cluster. Each level contains a different balance of gravity, motion, matter, and expansion. The Milky Way's 100,000 light-year disk seemed almost impossibly large. The local group stretches that scale to roughly 10 million light-years. And even the local group is only a small feature beside the structures beyond it. Farther out are richer clusters containing hundreds or thousands of galaxies. Between clusters are filaments extending across tens or hundreds of millions of light-years. Around those filaments lie immense regions of lower density. The map stops looking like a collection of islands and begins to resemble a web. Our galaxy becomes one point inside one group, inside one strand, inside a pattern covering a significant portion of observable space. The local group is the first larger home beyond the Milky Way. But it is not the largest structure. It is only the first place where the galaxy stops being the main subject and becomes one member of something wider. The cosmic web is not a poetic comparison added to make the universe sound mysterious. It is a physical pattern revealed by mapping the positions of galaxies across enormous distances. A photograph of a small region of sky may make galaxies appear scattered almost randomly. Some lie nearby. Others are far behind them. A flat image compresses those distances onto one surface and hides the deeper organization. When astronomers estimate distance through redshift and other measurements, the galaxies form a three-dimensional map. They do not fill space evenly. They gather along broad filaments. Those filaments meet at dense intersections containing groups and clusters. Between them are large regions with much less matter. The result resembles an irregular network surrounding dark cavities. This pattern began developing when the universe was much younger. The early cosmos was remarkably smooth, but it was not perfectly uniform. Some regions contained slightly more matter than others. The differences were small, yet gravity had billions of years to amplify them. A region with a little more matter exerted slightly stronger attraction. It drew in additional material. As it gained mass, its gravity strengthened. Less dense regions gradually lost matter to their surroundings and became emptier. Over time, this uneven growth produced galaxies, clusters, filaments, sheets, and voids. Dark matter played a central role. Because it does not interact strongly with ordinary light, it could form gravitational concentrations without being affected by pressure and radiation in the same way as hot gas. It created an invisible framework. Ordinary matter fell into that framework. Gas collected inside dark matter halos. In suitable regions, it cooled and collapsed. Stars formed. Galaxies assembled. The luminous cosmic web traced by galaxies is therefore only the visible part of a much larger distribution. A galaxy cluster occupies one of the dense nodes. Some clusters contain hundreds or thousands of galaxies moving inside a shared gravitational environment. But the galaxies do not contain all the cluster's ordinary matter. Much of it lies between them as extremely hot gas. This gas can reach millions of degrees and emit strongly in X-rays. Even that gas cannot explain the cluster's full gravity. The motion of galaxies and the bending of background light show that most cluster mass is dark matter. Gravitational lensing helps reveal it. A massive foreground cluster bends light from galaxies behind it. Those background objects may appear stretched into arcs, magnified, distorted, or repeated. By measuring the distortions, astronomers can estimate how mass is distributed, including mass that emits no light. A cluster is therefore more than a gathering of visible galaxies. It is a large common halo of dark matter and hot gas, several million light-years wide, containing many luminous systems. A rich cluster may contain more mass than hundreds of Milky Ways. Yet clusters are only knots in the larger web. Filaments can extend for tens or hundreds of millions of light-years. They are not narrow cords with clean surfaces. They are broad regions where matter and galaxies are more concentrated than in the surrounding space. Some connect major clusters. Others form sheets and walls containing vast numbers of galaxies. The word wall can be misleading. These structures are not solid barriers. Their galaxies remain separated by enormous distances. The name describes the overall arrangement, not a continuous object. At this level, gravity and expansion compete in a new way. Within a rich cluster, gravity can hold the system together. Within smaller groups, it can maintain a shared future. Across an entire supercluster, however, the structure may be too large and too loosely connected to collapse into one object. Different regions can belong to the same visible pattern while moving apart over cosmic time. Large-scale structure is not simply a hierarchy of increasingly larger bound objects. The universe reaches a scale where patterns remain visible without forming one permanent gravitational system. Between the filaments lie voids. A cosmic void is not absolutely empty. It can contain thin gas, dark matter, and scattered galaxies. But it contains far less matter than the surrounding filaments in clusters. Some voids span tens of millions of light-years. Larger void regions can extend even farther, depending on how their boundaries are defined. Imagine entering one. The local group has already shrunk into a nearly invisible detail behind us. The nearest major filaments may lie far away. Galaxies become sparse and faint. The sky beyond any local stars could appear unusually empty, A civilization developing inside a deeply isolated void galaxy might find it harder to discover the larger cosmic pattern. Nearby galaxies would be rare. The evidence for the cosmic web would arrive through extremely faint signals from great distances. Our own location is quieter than the center of a rich cluster, but it is not completely isolated. The Milky Way belongs to a modest group within reach of larger structures. This gives us access to nearby companions while still allowing a broad view of the universe beyond. Now compare the scales. The bright disk of the Milky Way is about 100,000 light-years wide. The local group spans roughly 10 million light-years. The distance to the Virgo cluster is measured in tens of millions. Major filaments and walls can extend across hundreds of millions. Hundreds or thousands of Milky Way widths can fit across a single large feature of the cosmic web. Yet the web does not build toward one final central object. When astronomers average the universe over sufficiently large scales, the distribution of matter becomes increasingly uniform. Clusters, walls, and voids remain visible, but no known location appears to be the center around which everything else is arranged. The universe has structure without a confirmed central point. That idea feels unfamiliar because most objects in ordinary life have centers. A planet has one. A star has one. A galaxy has a dense central region. Even a cluster may have a gravitational core. The observable universe is different. We see ourselves near the center of our observable region because light reaches us from every direction. An observer in a distant galaxy would also appear to occupy the center of their own observable region. Neither location is known to be the center of the entire universe. Each is the center of what can be observed from that position. This distinction determines the final comparison. We have moved from Earth through the Milky Way, the local group, clusters, filaments, and voids. But all these structures occupy only part of the region whose signals have reached us. To understand how much larger that region is, we need to define the observable universe. And we need to separate it from the whole universe, which may extend far beyond any light we can receive. The observable universe is the region from which a signal moving no faster than light has had enough time to reach us. The definition sounds simple. Almost every word requires care. Obviously does not mean that we have already photographed every object inside it. Some sources are too faint for present instruments. Some are hidden behind dust. Some matter emits little or no light. Some structures are known only through gravity. The word refers to a physical limit, not the strength of one telescope. It describes the region that could, in principle, have influenced our location since the beginning of cosmic history. We see the moon a little more than 1 second in the past. We see the sun about 8 minutes in the past. We see nearby stars several years in the past. We see Andromeda as it was roughly 2.5 million years ago. When telescopes detect galaxies billions of light years away, they receive light released before Earth existed. Looking farther into space means looking farther into time. Astronomy does not present the universe everywhere at one shared moment. It gathers delayed messages from different eras. Nearby objects appear relatively recent. Distant galaxies appear younger. The deepest observations become records of the early universe. This delay is often described as look-back time. If light has travelled for 10 billion years, we observe the source with a look-back time of roughly 10 billion years. But that does not mean the source is now 10 billion light-years away. The universe changed while the light travelled. Space expanded. The distance between large, unbound regions increased. A photon can spend billions of years moving toward us, while the present separation from its source becomes much greater than the simple travel time suggests. The observable universe is shaped by both light speed and expansion. It also depends on the universe having a finite age. Current cosmological evidence indicates that the hot, expanding universe is about 13.8 billion years old. Ordinary light, however, did not travel freely through all of that history. The earliest universe was extremely hot and dense. Matter existed as a charged plasma. Photons repeatedly scattered from free electrons and could not cross great distances in straight paths. The young cosmos was opaque. As expansion continued, the universe cooled. Roughly 380,000 years after the beginning of the hot early phase, electrons combined with nuclei to form neutral atoms. Photons could then travel much more freely. That ancient radiation still surrounds us. Expansion stretched it into microwave wavelengths, producing the cosmic microwave background. It is the oldest electromagnetic light we can observe directly across the sky. The cosmic microwave background does not mark the beginning of the universe. It marks the earliest surface ordinary light can reveal directly. We can learn about earlier periods through their effects, through particle physics, through gravitational signals, and through tested models. But a conventional telescope cannot simply look through the opaque plasma and photograph an earlier scene. The microwave background forms something like a visible inner surface around us. The word surface is only a description of the arriving light. There is no material shell surrounding the Milky Way. It represents locations from which the oldest freely traveling photons are reaching us now. An observer in another galaxy would see a different microwave background surface centered on that location. Earth is not known to occupy a privileged point. We appear central because every act of observation extends outward from the observer. Imagine people standing far apart while signals travel through a fog. Each person can receive only the signals that have had enough time to reach them. Their visible regions overlap, but they are not identical. The same principle applies in cosmology, though expanding space makes the geometry far more complex. Our observable universe is centered on us only in this observational sense. It is not known to be centered on the Milky Way physically. Observers in another galaxy would define their own observable region. They would see some structures we can see, some we cannot, and they would miss regions visible from Earth. No observer receives a complete universal view. Every observer is limited by location, time, and the speed of information. The boundary of this region is called a cosmic horizon. It is not a wall. A spacecraft could not arrive there and touch a surface. The horizon depends on the observer and the cosmic time of observation. As time passes, signals from some more distant regions can arrive for the first time. But expansion creates another limit. Some galaxies are now so distant that light they emit today may never reach us. We can observe their ancient history while becoming permanently disconnected from their future. This seems contradictory only when past and present distance are treated as the same thing. The light entering our telescopes left long ago, when the expansion history and separations were different. A galaxy's past can remain visible even when its present activity cannot influence our remote future. This gives us several distinct ideas. Visible does not mean reachable. Reachable in principle does not mean reachable with current technology. Look-back time is not the same as present distance. The observable universe is not necessarily the entire universe. And the cosmic horizon is not a physical edge where existence stops. Without these distinctions, it is easy to imagine the observable universe as a sphere floating inside nothing. We might picture the Milky Way near the center and a final boundary surrounding everything. That picture is unsupported. The sphere belongs to our perspective. Beyond our horizon, there may be more galaxies, more filaments, more voids, and more space following the same general laws. Those regions are not known to be absent. Their information simply has not reached us. This is why science cannot give a confirmed measurement for the total size of the universe. It can estimate the scale of the observable region. It can test the geometry of space. It can reconstruct the history of expansion. But the whole universe may be far larger than what we see. It may even be infinite. For our comparison with the Milky Way, precise language matters. We should not say that all of existence is exactly 93 billion light-years wide. We can say that the observable universe has a present diameter of roughly that size, according to the expansion history supported by current evidence. The radius is not simply 13.8 billion light-years. The diameter is not simply twice the age expressed as distance. The reason is that space expanded while ancient light travelled. Matter whose radiation has been moving toward us for most of cosmic history is now much farther away than its travel time alone would suggest. The observable radius is about 46.5 billion light-years in present distance terms. Its diameter is therefore roughly 93 billion. That creates the central puzzle of the next step. How can a universe about 13.8 billion years old contain an observable region approximately 93 billion light-years across? The answer does not require light to break its speed limit. It requires us to understand that the distance itself changed during the journey. The figure seems impossible only if we imagine light crossing a static universe. If space had remained unchanged since the earliest light began travelling toward us, then a universe 13.8 billion years old could not reveal anything more than about 13.8 billion light-years away in each direction. Its observable diameter would be roughly twice that distance. That space did not remain fixed. While ancient photons travelled toward the region that later formed the Milky Way, the separation between large, unbound parts of the universe continued to increase. Light moved through expanding space. At every local point, the photon travelled at the speed of light relative to its immediate surroundings. It did not become faster. The scale of the path changed. A common analogy imagines an insect walking across an elastic strip while the strip stretches. The insect moves at a constant local speed, yet the total distance between the beginning and end increases during the journey. The comparison is imperfect. The universe is not a sheet expanding into a surrounding room. Galaxies are not objects glued to rubber. Still, the analogy captures one essential idea. A signal can travel for 13 billion years while the present distance to its source becomes much greater than 13 billion light-years. In an expanding universe, distance has several meanings. One measure describes how long the light has travelled. Another helps determine how large an object appears. Another relates observed brightness to intrinsic brightness. Another estimates how far away the source would be now according to a shared cosmological model. These quantities are connected, but they are not identical. For our size comparison, the most useful measure is the present distance to the matter at the edge of our observable region. That matter is now roughly 46.5 billion light-years away. Double the radius, and the observable diameter becomes about 93 billion light-years. The light did not cross 46.5 billion light-years of fixed space. It began its journey when the source was much closer to the region that would become our location. As the photon moved, the universe expanded, increasing the present separation. Expansion also stretches wavelengths. This produces cosmological redshift. Light emitted at shorter wavelengths can arrive at longer wavelengths after travelling through expanding space. Visible light from a distant galaxy may shift into infrared. Radiation released in the young universe now reaches us in microwave form. The cosmic microwave background provides the clearest example. When those photons began traveling freely, the universe was filled with radiation associated with a temperature of thousands of degrees. Billions of years of expansion stretched the wavelengths. Today, the radiation has a temperature of about 2.7 degrees above absolute zero. It fills the sky as a faint microwave background. The photons did not simply lose energy through ordinary friction. Their wavelengths expanded with the universe. Redshift allows astronomers to reconstruct cosmic history. It helps estimate how much the universe has expanded since particular light was emitted. Combined with other observations, it connects the distant objects we see with the changing scale of space. But redshift is not a perfect distance label by itself. Nearby galaxies can have local motions shaped by gravity. Andromeda is approaching the Milky Way in radial motion even though the universe expands on larger scales. Across the local group, gravity dominates, At greater distances, the overall expansion becomes increasingly important. On average, more distant galaxies show greater cosmological redshift. This relationship provided early evidence that the universe is expanding. The expansion rate has not remained constant. It cannot be described accurately by taking the present rate and running it backward in a simple line. Radiation, matter, dark matter, and dark energy influence the expansion differently during different eras. In the early universe, radiation played a larger role. Later, matter dominated the growth of structure. In the more recent cosmic era, observations indicate that expansion has accelerated. The standard cosmological model attributes this behavior to dark energy. The phrase is a name for the observed effect and its mathematical treatment. It is not a final explanation of what the cause fundamentally is. Accelerated expansion changes the future of visibility. Some galaxies whose ancient light reaches us today are now separated from us in such a way that signals they emit at the present cosmic time may never arrive. Their recession can exceed the speed of light without violating the local speed limit of relativity. An object cannot move through its nearby space faster than light. Cosmological expansion describes the changing distance between widely separated locations. Enough space can expand between us and a galaxy that the total separation grows faster than a light signal can close it. No local observer sees the galaxy racing past at several times light speed. The effect belongs to the large-scale geometry. This gives cosmology several important horizons. The particle horizon describes the greatest distance from which signals have reached us since the early universe. A cosmic event horizon describes regions from which signals emitted now or later will never reach us. The Hubble radius identifies a scale related to the present expansion rate. These are not the same boundary. For our comparison, the particle horizon determines the present observable radius of roughly 46.5 billion light-years. But the journey now changes its intellectual task. Until this point, we have asked how many Milky Way widths fit across observable space. That is a one-dimensional comparison. The universe extends in every direction. Galaxies occupy volume. If one sphere is 10 times wider than another, its volume is about 1,000 times greater. If it is 100 times wider, its volume is about 1 million times greater. If it is nearly 1 million times wider, the volume difference rises toward a number that ordinary language barely handles. The observable universe is roughly 930,000 times wider than a 100,000 light-year Milky Way disk. If we represent both as comparable three-dimensional regions, the volume ratio rises toward 800 quadrillion. That does not mean 800 quadrillion Milky Ways actually exist. Galaxies are not identical spheres. They are separated by immense gaps. Their halos vary and overlap. The cosmic web is uneven. The calculation is a scale comparison, not a galactic census. To estimate the actual number of galaxies, we need evidence. We must observe small regions of sky, measure faint objects across cosmic time, correct for sources too dim to detect directly, and decide how representative each survey is. The next step is therefore no longer pure geometry. It is the difficult process of counting galaxies in a universe whose most distant populations appear as tiny traces of ancient light. The evidence begins with a region of sky that appears almost empty. In the mid-1990s, the Hubble Space Telescope spent many hours observing a tiny patch near the constellation Ursa Major. The field contained no bright nearby stars and no obvious large galaxies. To the unaided eye, it would have looked like ordinary darkness. Hubble continued gathering light. Exposure after exposure was combined until faint objects emerged. The final Hubble Deep Field revealed thousands of distant galaxies inside a patch only a few arc-minutes wide. Almost every small point, smear, and colored shape was an entire galaxy. The image transformed cosmic scale into something visible. Instead of showing one spectacular spiral, it presented layers of galactic history compressed into one narrow view. Some galaxies were relatively nearby. Others appeared as they existed when the universe was much younger. Some were irregular and actively forming stars. Others had more developed forms. Their colors and shapes recorded different stages of evolution. The darkness had not been empty. Our instruments had simply failed to collect enough of its light. Later observations went deeper. The Hubble Ultra-Deep Field concentrated on another tiny region for even longer. Additional surveys used improved detectors, wider fields, and different wavelengths. Infrared observations became essential because expansion shifts light from very distant galaxies toward longer wavelengths. The James Webb Space Telescope extended this method with a large infrared mirror and instruments designed to study the early universe. Webb detects galaxies whose light has traveled for more than 13 billion years. These distant systems do not always resemble mature nearby spirals. Many appear compact, irregular, faint, or unusually active. Their light began traveling while galaxies were assembling rapidly. But a deep field image is not a photograph of the whole universe. It is a sample. Imagine estimating the number of trees across an entire continent by examining one carefully chosen square of forest. The square may contain thousands of trees, but the final estimate depends on whether it represents other regions. Astronomers face a similar problem on a far larger scale. They observe selected patches of sky. They identify galaxies at different brightness levels. They estimate distances. They calculate how much cosmic volume the survey represents. Then they correct for galaxies too faint, too small, or too distant to be detected directly. Every stage introduces uncertainty. Some galaxies overlap in a flat image. Some hide behind brighter foreground sources. Some contain active black holes that make them unusually luminous. Dust can absorb shorter wavelengths and re-radiate energy in infrared. A galaxy's apparent brightness depends on distance, age, star formation, dust, size, orientation, and the wavelengths measured. Even defining a galaxy becomes difficult near the detection limit. A faint concentration of stars may be a separate dwarf system. It may be a star-forming region inside a larger galaxy. Several bright knots may belong to one irregular object rather than several independent ones. A source may appear clearly in one observation and disappear into noise in another. Researchers do not simply count dots. They build statistical models. One key tool is the galaxy luminosity function. It describes how many galaxies exist at different brightness levels during a particular cosmic era. Bright galaxies are easier to detect but relatively rare. Faint galaxies are far more numerous and easier to miss. A survey may reveal the bright population directly. Astronomers then estimate how far the distribution continues below the detection threshold. The result depends strongly on the abundance of faint galaxies. This is why estimates of the total galactic population vary. A commonly repeated older scale placed the number around 100 billion. Later analyses argued that the observable universe may contain far more, potentially reaching into the trillions if very faint and early systems are included. These figures do not necessarily describe the same population. One estimate may count galaxies bright enough to be observed individually under a particular definition. Another may include vast numbers of small systems inferred statistically. Galaxies also merge. The universe may have contained more separate small galaxies in the past than it contains today. Many combined to form larger systems. The present Milky Way is not one unchanged object that has existed since the earliest era. It grew through gas accretion, star formation, internal evolution, and repeated mergers. So the question of how many galaxies exist does not have one timeless answer. The number depends on when we count. It depends on how small a system can be and still qualify as a galaxy. It depends on whether we count only individually detected objects or include populations inferred below current limits. The strongest conclusion is not one exact figure. It is that the Milky Way is one galaxy among an enormous population spread across observable space. Even a conservative count is difficult to absorb. Suppose there were only 100 billion galaxies. That would already place the galactic population near the estimated number of stars in the Milky Way, depending on which stellar estimate we choose. But galaxies are not identical copies of our own. Many are smaller dwarf systems. Some contain relatively few stars. Others are giant ellipticals with masses far exceeding the Milky Way. Some actively form stars. Others contain little cold gas and have largely stopped. Some are isolated. Others move through dense clusters where gravity and hot surrounding gas reshape them. The Milky Way occupies a middle position. It is a large spiral, but not the largest galaxy known. It is more massive than most dwarfs, yet smaller than the greatest giant galaxies near rich cluster centers. Now imagine expanding one deep field until it covers the whole sky. The number of narrow patches required would be enormous. Each would contain galaxies at many distances and stages of development. Nearby systems would occupy larger angular areas. Distant galaxies would appear as faint marks. Behind those would be populations too dim for direct detection. This is the observational foundation beneath the scale comparison. We infer the enormous galactic population from repeated surveys, deep exposures, redshift measurements, infrared observations, lensing, and statistical correction. Gravitational lensing can expose sources otherwise too faint to see. A massive foreground cluster bends and magnifies the light of galaxies behind it. But lensing also complicates the count. Magnification varies. One galaxy may appear in several images. Researchers must model the foreground mass to reconstruct the source. Every faint object passes through layers of interpretation. Its distance must be estimated. Its brightness must be corrected. Its classification must be tested. This careful process is less dramatic than declaring one perfect number. It is also more trustworthy. It shows how knowledge can be extracted from a small number of photons after a journey lasting most of cosmic history. The darkest regions of the sky have become evidence. They show that the Milky Way is not surrounded by only a few neighboring systems. It belongs to a universe whose galactic population extends through almost every direction and almost every observable era. Counting those galaxies, however, still does not reveal the complete contrast. We now need to examine the simplest size ratio and understand what that arithmetic leaves out. The central calculation uses two familiar estimates. The bright stellar disk of the Milky Way is roughly 100,000 light-years across. The observable universe is roughly 93 billion light-years across in present distance terms. Dividing the second number by the first gives a ratio of approximately 930,000. The arithmetic is simple. The meaning is not. The first limitation is the definition of the Milky Way. We chose 100,000 light-years because it is a useful width for the bright disk. But the galaxy extends beyond it. Faint outer stars reach farther. The stellar halo reaches farther again. Hot gas surrounds the system. The dark matter halo may span several 100,000 light-years in radius, depending on the chosen boundary. If we compare the observable universe with the extended dark matter halo rather than the bright disk, fewer galactic widths fit across it. The ratio might fall from nearly 1 million to a few 100,000. The conclusion remains overwhelming, but the number depends on which part of the galaxy we call its edge. The second limitation is the observable diameter. 93 billion light-years is not a distance measured by placing a ruler across the cosmos. It is inferred from observations and a cosmological model. Astronomers estimate the age and expansion history of the universe using several independent forms of evidence. These include the cosmic microwave background, galaxy redshifts, exploding stars used as distance indicators, and large-scale patterns in the distribution of matter. Together, these measurements support a present observable radius of roughly 46.5 billion light-years. But the estimate depends on our model of expansion. Researchers must determine how radiation, matter, dark matter, and dark energy influenced cosmic history. They compare different observations and test whether they agree. The broad scale is well supported, but it should not be treated as a hard wall known to the final kilometre. The third limitation is that the Milky Way and the observable universe are different kinds of things. The Milky Way is a gravitationally bound system. The observable universe is a region defined by the travel of information to an observer. One has a physical identity shaped by gravity. The other has an observational boundary shaped by cosmic history. The Milky Way would remain a galaxy even if no observer existed on Earth. Our observable region is specifically the part of the cosmos whose signals have reached our location by the present time. An observer in another galaxy would define a different observable sphere. Most of it might overlap with ours if the observer were nearby on cosmic scales. Its most distant boundaries would not be identical. The ratio compares a physical structure with an observer-dependent horizon. It is useful, but it is not a comparison between two objects of the same category. The fourth limitation is geometry. A diameter tells us how many Milky Way widths fit along one line. It does not describe the full three-dimensional difference. If we imagine a sphere 100,000 light-years across, then a sphere 930,000 times wider has a volume larger by approximately the cube of that ratio. The result is about 800 quadrillion. That is roughly 8 followed by 17 zeros. But this does not tell us the number of real galaxies. The Milky Way is not a perfect sphere. The observable universe is not packed with galaxies like objects in a box. Most of the volume between galaxies contains no stars. Galaxies vary widely in size. Their dark matter halos overlap inside groups and clusters. The volume calculation is a mathematical demonstration of scale, not a physical packing estimate. The fifth limitation is time. When we describe the observable universe as 93 billion light-years across today, we use present distances inferred through the standard model. But we do not see the most distant regions as they are today. We see ancient light. The farthest visible matter appears as it existed when the universe was extremely young. Nearby galaxies appear more recently. The cosmic map combines many periods into one view. It is not a photograph of one universal moment. The Milky Way is also seen through delayed light, but the delay across the disk is measured in tens of thousands of years. Across observable space, the delay reaches billions. The two scales carry different relationships between distance and history. The sixth limitation is accessibility. The Milky Way is large, but its parts remain within one broad gravitational environment. A signal can cross the disk in principle, even if it requires tens of thousands of years. Much of the observable universe cannot be reached by any signal we send now. We can receive ancient light from galaxies whose present regions are already beyond our future communication horizon. They are visible in the past, but unavailable to our future. The observable universe is therefore larger than the region with which Earth can ever exchange information. Finally, the ratio says nothing certain about the full universe. The observable region may be only one portion of a much greater whole. If the universe is infinite, no finite number of Milky Way widths could span it. If it is finite but much larger than our horizon, the true ratio could exceed 930,000 by an unknown amount. These limitations do not weaken the comparison. They prevent us from turning a useful number into a false certainty. The bright Milky Way disk gives us a practical ruler. The observable diameter gives us a practical horizon. Between them lies a ratio close to 1 million. But the number must carry its conditions. It compares the bright disk not every possible galactic boundary. It compares with observable space, not necessarily all existence. It uses present distance terms for a universe seen across many different ages. And it describes width, not volume, reachability, or the actual number of galaxies. Once those conditions are understood, the ratio becomes more powerful. It is no longer just a large figure. It is a disciplined answer showing how far our knowledge extends and where uncertainty begins. The next question is what this difference means for any civilization living inside the Milky Way. A universe can be visible at one scale and accessible at another. The gap between those two regions may define the deepest practical limit hidden inside the title. Human history trained us to expect technology to defeat distance. A mountain can be crossed. An ocean can be crossed. A journey that once required months can later require hours. Radio reduced communication across Earth to fractions of a second. The universe does not fully follow that pattern. Technology can increase speed, improve navigation, extend survival, and allow machines to endure hostile environments. But no known method allows matter or information to move locally faster than light. That limit changes the meaning of exploration. Within the solar system, delayed communication is already unavoidable. A signal to the moon takes a little more than 1 second each way. Mars can be several light minutes from Earth, depending on the positions of the planets. Commands to distant spacecraft may require hours to arrive. Engineers cannot guide a rover on Mars as though controlling a machine beside them. The rover must make some decisions on its own. As distance increases, autonomy becomes more important. Across interstellar space, delay becomes the central condition. A probe at the nearest star would send information requiring more than 4 years to return. A question and answer between Earth and a settlement there would take close to a decade. At 100 light-years, a complete exchange would span 2 centuries. Across the Milky Way, communication becomes a message between eras. A civilization near the far side of the disk could transmit a signal today, yet Earth might receive it tens of thousands of years from now. A reply would take tens of thousands more. The senders might no longer exist. Neither might we. This creates a biological limit before an engineering one. Human lives are brief compared with interstellar travel. Even a voyage lasting several centuries would outlive its original crew. A mission would require long-duration life support, suspended biology, radical life extension, artificial intelligence, self-repairing machines, or generations born during the journey. Each possibility introduces risks beyond propulsion. A generation ship would need to preserve air, water, food, energy, medicine, education, and social stability across centuries or longer. Its destination could be studied only through old information. By the time the travelers arrived, conditions might differ. A star could be more active than predicted. A planet's atmosphere could prove unsuitable. Resources might be inaccessible. A technical weakness tolerable during a decade could become fatal over a millennium. Distance magnifies uncertainty. A civilization spreading gradually through the Milky Way would also face fragmentation. Settlements separated by hundreds or thousands of light-years could not share one immediate political life. Languages would change. Cultures would diverge. Technologies might develop along different paths. By the time instructions reached a distant colony, the authority that sent them could be ancient history. A galactic civilization would probably resemble a family of related societies rather than one coordinated empire. Shared ancestry could survive. Immediate control could not. The size of the Milky Way imposes decentralization. Intergalactic travel moves the problem into another category. Andromeda lies about 2.5 million light-years away. A hypothetical vessel traveling at 10% of light speed would need roughly 25 million years to cross that distance in the external frame, before accounting for acceleration and slowing. 25 million years ago, our ancestors were not human. Continents occupied different positions. Entire groups of animals had not yet evolved into their familiar forms. A species launching such a mission could not expect to greet the travelers at the destination. The journey would be released into deep time. At speeds close to light, relativity could reduce the time experienced on board. But energy requirements would rise enormously. A small particle striking the craft could release devastating energy. Radiation would threaten biology and electronics. Navigation would need extraordinary precision. A target galaxy would move during the voyage. The engineering problem is not simply a faster engine. It is survival inside a hostile relationship between speed, matter, time, and energy. The observable universe makes even Andromeda seem local. Most of its galaxies lie far beyond any plausible journey. Many are beyond our cosmic event horizon. No signal sent from Earth now will ever reach them. Their ancient light enters our telescopes. Their future cannot enter our history. This creates a strange form of separation. We can know that a distant galaxy existed. We may estimate its mass, star formation, chemical composition, and distance. We may observe it during an early stage of development, but we cannot affect it. We cannot send a message that will arrive. We cannot join its future under ordinary light-speed limited physics. Humanity can see farther than humanity can ever travel. Cosmic scale can make a human life feel insignificant. The Milky Way is one galaxy among an enormous population. The observable universe is nearly 1 million galactic widths across. A person occupies almost no measurable fraction of that map. But physical size and significance are not the same property. A living cell is smaller than a mountain, yet it can reproduce and carry information. A brain is smaller than a planet, yet it can reconstruct planetary motion. The universe contains structures vastly larger than us. Our minds are among the few confirmed places where those structures are compared and understood. That does not prove humanity is unique. The universe is too large, and our search too incomplete for certainty about other intelligence. But from one planet, human beings have detected radiation older than the present form of the Milky Way. We have measured expansion. We have inferred dark matter through gravity. We have reconstructed the early universe from microwave patterns. We have observed galaxies whose light travelled for most of cosmic history. Our smallness did not prevent understanding. It made understanding difficult and valuable. The scale comparison also changes the meaning of survival. A civilization limited to one planet is vulnerable to one planetary disaster. A civilization spread across several worlds is harder to erase. A civilization established around many stars becomes more resilient still. But even a galaxy-spanning society would occupy a tiny fraction of observable space. The Milky Way may contain enough stars and planets to support forms of life and culture beyond anything we can imagine. We have explored almost none of it. Before worrying that the universe is too large to cross, humanity has not crossed the gap to the nearest star. Our immediate frontier is not the cosmic horizon. It is the darkness just beyond the solar system. The observable universe gives us the largest possible map. The Milky Way gives us the most realistic long-term territory. And the distance between those two ideas tells us that seeing a place is not the same as being able to enter its story. The universe visible to our telescopes and the universe available to our future are not the same size. That distinction becomes clearer as cosmic time passes. The Milky Way continues to evolve. It forms stars, exchanges gas with its surroundings, and interacts with satellite galaxies. The local group also evolves under gravity. Its members are not fixed points on a permanent map, yet the region is likely to remain gravitationally connected even while more distant structures recede. The long-term relationship between the Milky Way and Andromeda illustrates the uncertainty. Their present radial motion brings them closer. Older models often described a future merger as nearly certain. Improved measurements have weakened that conclusion. Small uncertainties in sideways velocity produce large differences after billions of years. The gravitational influence of Triangulum in the Large Magellanic Cloud can also alter the result. Current models allow a close encounter, a merger, or a longer separation. The collision probability over the next 10 billion years appears closer to 50-50 than inevitable. Whatever happens between the two largest galaxies, the local group remains a special gravitational island. Its major members are close enough, and its total mass is great enough, that cosmic expansion does not simply carry them apart like distant, unbound galaxies. Over very long periods, some members may merge, others may settle into wider orbits. Dwarf galaxies may be stripped or absorbed. The exact arrangement can change, while the larger group remains connected. Beyond the local group, the future becomes different. The expansion of space is accelerating. Distant galaxy groups and clusters not bound to us will recede more rapidly. Their light will stretch to longer wavelengths. Their apparent brightness will decline. Signals emitted by many of them in the present cosmic era will never reach the Milky Way. We can still receive older light already traveling toward us. For billions of years, photons released in the past will continue arriving. But the later histories of those galaxies will remain inaccessible. More of the wider universe will fade beyond practical observation. This does not mean the observable radius simply shrinks. Cosmological horizons evolve in different ways. The region that has already influenced us can continue growing in one sense as more ancient signals arrive. At the same time, the set of galaxies whose new light will ever reach us can become more restricted. The visible past can expand while the accessible future contracts. For observers living in an extremely distant era, the merged or rearranged local group may appear almost alone. Other clusters could have faded beyond detection. The cosmic microwave background would be stretched to wavelengths so long and energies so low that observing it could become extraordinarily difficult. Evidence that is available to us today might be nearly erased from their sky. Those future astronomers could live inside one enormous galaxy and see little beyond it. Without preserved records, they might struggle to discover that the universe once revealed a vast web of distant structures. They could mistake their local island for the greater cosmos. We live during a period when several layers of cosmic history remain observable. Nearby galaxies can be studied in detail. Distant galaxies appear at earlier stages of development. The microwave background reveals the young universe. Large-scale surveys map the web between. This timing does not imply that our era was planned or privileged. It means only that the evidence currently available is unusually rich. We can compare bound structures with cosmic expansion. We can observe galaxies that are already beyond future contact. We can see farther than any civilization could travel. The observable universe is roughly 93 billion light-years across in present distance terms. But the region a civilization from Earth could ever reach is far smaller. Even under extremely optimistic assumptions, movement remains limited by light speed, energy, time, and expansion. The local group may define the broadest gravitational environment that remains connected to our future. The Milky Way, or whatever system it becomes after billions of years of interaction, may contain almost the entire practical domain available to distant human descendants. This gives the title a deeper answer. The universe is much larger than our galaxy in observable scale, but our galaxy may contain a large fraction of the future we could ever physically join. The contrast is not only between a small disk and a vast horizon, it is between knowledge and participation. Telescopes allow us to receive ancient information from enormous distances. Physics prevents us from turning all that information into a travel map. The galaxies in a deep field are real. Their light reaches us, but many cannot receive anything we send. The cosmic web can be measured without becoming a road network. The horizon can be studied without becoming a destination. Our galaxy therefore carries two opposing meanings. Against the observable universe, it is tiny. Against the region available to human exploration, it is overwhelming. 100,000 light-years already contain more stars, planets, environments, and possible histories than our species could examine across any familiar timescale. A million-year project would still reveal only part of it. A civilization surviving for billions of years might watch the local group transform, while the wider universe slowly disappears from contact. the observable map would remain in records, mathematics, and ancient light. The lived territory would become more local. This does not reduce the value of looking outward. Observation is a form of contact, even when response is impossible. A photon reaching Earth from a distant galaxy carries evidence of stars that lived before the Sun existed. It connects two regions through history, though not through shared future communication. The telescope turns separation into knowledge. The galaxy turns that knowledge into perspective. The Milky Way is not merely a small object inside a larger universe. It is the environment from which the larger universe becomes visible. Its stars created the elements used to build Earth. One of those stars supplied the energy that allowed life to develop. That life eventually built instruments capable of receiving messages from the cosmic horizon. The visible universe may be almost 1 million Milky Way widths across. The accessible future may remain close to one galactic neighborhood. Both statements can be true. One describes the reach of light arriving from the past. The other describes the reach of anything we might send into the future. And between them lies the strange position of an observer who can understand far more space than it can ever enter. We can now state the comparison in its strongest form. The bright stellar disk of the Milky Way is roughly 100,000 light-years across. The observable universe is roughly 93 billion light-years across in present distance terms. Divide the larger figure by the smaller. The result is approximately 930,000. So the observable universe is nearly 1 million Milky Way disk widths across. Not 1,000, not 10,000. Nearly 1 million. If the Milky Way were reduced to a disk 1 centimeter wide, the observable universe would extend for about 9.3 kilometers. Our galaxy would become a tiny mark inside a landscape stretching beyond ordinary walking distance. The solar system would be too small to see. Earth would vanish completely, and the 1 centimeter Milky Way would not stand alone. The model would contain an immense population of other galaxies. Some would be dwarf systems far smaller than ours. Others would be giant galaxies containing more mass and more stars. They would gather into groups and clusters. The clusters would trace filaments. The filaments would surround enormous voids. Most of the 9-kilometer model would still appear empty. That darkness is part of the answer. The observable universe is not large because galaxies are packed tightly together. It is large because the structures and the distances between them extend across scales that exceed our galaxy again and again. Now reverse the model. Imagine the observable universe reduced to a region 93 kilometers wide. At that scale, the bright disk of the Milky Way would measure about 10 centimeters. A galaxy containing hundreds of billions of stars would fit across the palm of the hand. The local group would span several meters. Large clusters would lie much farther away. Filaments would extend across substantial parts of the landscape. The full model would continue for nearly 100 kilometers. This does not make the Milky Way small in any absolute sense. It reveals how much larger the surrounding scale is. The same contrast appears through light travel time. Light needs roughly 100,000 years to cross the Milky Way's bright disk. If space were fixed and the full route were physically available, light would need 93 billion years to cross a distance equal to the present observable diameter. That simplified journey would last more than 6 times the current age of the universe. In reality, no photon can travel from one present edge of our observable region to the other as though crossing a static container. Space expands. The distant boundaries belong to different observer perspectives. Much of the route is causally inaccessible. Still, the travel time image reveals the scale. Crossing one Milky Way is already a project longer than the existence of our species. Crossing nearly 1 million such widths belongs to another order of thought. The ladder between them matters. From Earth to the outer solar system, light travel is measured in hours. To nearby stars, it is measured in years. Across the Milky Way, it is measured in tens of thousands of years. To Andromeda, it is measured in millions. Across the local group, the distance reaches roughly 100 galactic widths. To major clusters, the count rises into hundreds. Across the largest features of the cosmic web, it rises into thousands, then tens of thousands. Finally, across observable space, it approaches 930,000. The universe does not jump directly from one galaxy to an incomprehensible edge. It unfolds through nested structures. Each level preserves the one below it while reducing its importance on the larger map. This ladder is the earned answer to the title. The Milky Way belongs to a group. The group occupies a small region of a wider network. The network extends through an observable volume nearly 1 million galactic disk widths across, but diameter still understates the contrast. If we imagine the Milky Way as a sphere 100,000 light-years across, and compare it with a sphere 93 billion light-years across, the volume difference rises with the cube of the width ratio. The result is about 800 quadrillion. Written out, it is approximately 800,000 trillion. This is not the number of galaxies in the observable universe. The Milky Way is a flattened disk inside a much larger halo. Galaxies are not packed without gaps. Their sizes vary enormously. Most cosmic volume contains extremely little luminous matter. The calculation reveals available scale, not actual population. That distinction explains why hundreds of billions or even trillions of galaxies can remain sparse. A deep field image may look crowded because light from many distances is compressed into one flat picture. In 3 dimensions, those galaxies are separated by enormous spaces and often belong to different cosmic eras. The image is crowded. The universe is not. The Milky Way provides a smaller version of the same illusion. It contains hundreds of billions of stars, yet the average distance between nearby stars is measured in light-years. From far away, those stars blend into one bright disk. From inside, the space between them dominates. Cosmic structure is built from luminous concentrations surrounded by darkness. There is one final condition attached to the answer. The figure 930,000 compares the Milky Way with the observable universe. It does not compare our galaxy with all existence. The total universe may continue far beyond our horizon. If space is infinite, no finite line of Milky Way disks could cross it. If the universe is finite but vastly larger than the observable region, the true ratio could still exceed our figure by an enormous amount. Current measurements show that the large-scale geometry of observable space is very close to flat. That does not prove infinity. A sufficiently large curved universe would appear flat within the small region we can measure, just as a small area of Earth appears flat beneath our feet. We strongest answer must therefore stop where the evidence stops. We can say that the observable universe is roughly 93 billion light-years across. We can say that this is about 930,000 times the width of the Milky Way's bright disk. We can say that the volume contrast is vastly greater. We can say that the total universe may be much larger. We cannot honestly say where all existence ends. No telescope has found a physical edge. No observation has revealed a final wall. The horizon marks the limit of arriving information, not the confirmed boundary of reality. The title's promise is now paid. Our galaxy is immense. The observable universe is nearly 1 million times wider, and the whole universe may exceed even that comparison by an amount we cannot yet measure. The remaining question is not how large the observable region is. It is whether any evidence inside that region can reveal the size of what lies beyond it. The honest answer is that the total size of the universe may remain unknowable. Every measurement begins inside our observable region. Every telescope receives information that has crossed a finite distance. Every experiment is performed within the same cosmic horizon. We cannot step outside the observable universe and look back. We cannot place a detector beyond the region from which signals reach us. Still, the unseen universe may leave indirect clues inside the part we can observe. One of the most important clues is cosmic geometry. On the largest scales, space can be positively curved, negatively curved, or very close to flat. A positively curved, two-dimensional surface is often compared with the surface of a sphere. Travel far enough in one direction, and a path can eventually return to its starting point. A negatively curved surface is often compared with a saddle. Parallel paths behave differently, and the geometry remains open. Flat space follows the familiar rules of ordinary geometry. Parallel lines remain parallel. The angles of a large triangle add in the expected way. These comparisons describe two-dimensional surfaces. The universe has three spatial dimensions. The analogies help us understand the concept, but they are not literal pictures of the cosmos. Astronomers test geometry through patterns visible across immense distances. One important pattern appears in the cosmic microwave background. The early universe contained waves of compression and expansion moving through hot plasma. When the cosmos cooled enough for light to travel freely, those waves left characteristic physical scales in the distribution of matter and radiation. Cosmological physics allows researchers to estimate the true size of these patterns. Observations show how large they appear across the sky. If space was strongly curved, the apparent angular size would differ from what a flat universe predicts. Measurements indicate that observable space is remarkably close to flat. This places limits on curvature. If the universe is finite, because it curves back on itself, the radius of that curvature must be much larger than the region we can observe. Imagine measuring a small patch of Earth. The ground appears flat because the planet is far larger than the area beneath us. In the same way, observable space may look flat because any overall curvature appears only across a scale beyond our horizon. Near flatness does not prove the universe is infinite. It means that a finite, curved universe would need to be very large. The whole cosmos could be many times larger than the 93 billion light-year observable region and still appear nearly flat from within it. Geometry is not the same as topology. Geometry describes curvature. Topology describes how space is connected. A universe can be geometrically flat and still possess a finite volume if its boundaries connect in a particular way. A simple analogy is a game map, where leaving through one side returns you through the opposite side. The surface can be locally flat while having a repeating global structure. Real cosmic topology could be far more complicated. If the universe was small enough and connected to itself, light might travel around it along more than one path. We could see repeated images of the same distant galaxy in different directions. The cosmic microwave background might contain matching patterns produced by the same physical region viewed through several routes. Astronomers have searched for such repetitions. No confirmed pattern has shown that observable space wraps around on a scale comparable with or smaller than our horizon. That does not prove that space has no repeating topology. The fundamental scale may simply be too large. The repeated images may lie beyond the region from which light has reached us. Another clue comes from cosmic inflation. Inflation describes a proposed period of extremely rapid expansion during the earliest moments of the universe. It was developed to explain several observed features, including large-scale smoothness, near-flat geometry, and the origin of small density variations that later grew into galaxies. The broad inflationary framework fits important evidence. Its exact physical mechanism remains uncertain. Different models propose different energy scales, durations, and consequences. In many versions, the region that became our observable universe began as only a small part of a much larger, expanding domain. If inflation continued much longer than the minimum required to explain observations, the entire universe could be enormously larger than our horizon. The observable cosmos would be one patch inside a far greater expanse. Some models allow inflation to continue in distant regions while ending locally. This can produce many separated domains with different histories or physical conditions. Such ideas are mathematically serious, but their most dramatic implications remain difficult to test. An inflationary multiverse is not a confirmed map. It is a consequence of some models, not an observed collection of other universes. The distinction matters. A model may explain current evidence while making predictions beyond direct observation. Scientists must ask which consequences are unique, which can be measured, and whether competing explanations produce the same visible result. Future evidence may come from signals older than ordinary light. More precise observations of the cosmic microwave background could reveal subtle patterns connected with early physics. Surveys of galaxies may improve measurements of curvature and expansion. Gravitational waves could provide information from periods hidden from electromagnetic telescopes. A primordial gravitational wave background, if securely detected, might carry evidence from an era far earlier than the release of the microwave background. But even such discoveries may not reveal the total size of the universe. They could support one model of early expansion. They could eliminate others. They might tell us more about how our observable region developed. The space beyond the horizon could remain inaccessible. There is a fundamental reason. Science distinguishes possibilities through observable consequences. If two different universes produce exactly the same measurable conditions inside our horizon, no experiment confined to our region can separate them. One universe may be finite, another may be infinite. One may continue uniformly beyond what we see. Another may change in ways that leave no detectable trace here. If their observable predictions are identical, the difference remains beyond empirical reach. This is not a failure of science. It is science recognizing the boundary of available evidence. Knowledge does not require pretending that every question already has an answer. Sometimes the strongest conclusion is a disciplined range of possibilities. We know the observable radius is roughly 46.5 billion light-years in present distance terms. We know observable space is close to flat. We know no physical cosmic edge has been detected. We know the entire universe must be at least as large as the region we observe. We also know that several serious cosmological models allow it to be much larger. What remains unknown is the factor the universe may exceed our horizon by a finite amount that will remain permanently hidden. It may be so large that observable space is only a minute fraction of the whole. Or it may have no finite spatial extent. Each possibility changes the largest scale in tonight's comparison. None changes our immediate position. The Milky Way remains roughly 100,000 light-years across in its bright disk. The observable universe remains nearly 1 million such widths across. Our galaxy remains one luminous structure inside a web extending toward every measurable horizon. The uncertainty begins only when we ask what lies beyond that horizon. We began inside a galaxy too large for any human journey. We crossed its disk in imagination, left its halo, entered the local group, followed clusters and filaments, and reached the limit of arriving light. Observation can take us no farther. The final step is to return through those scales and ask what the comparison leaves behind in the mind. We have travelled as far outward as observation currently allows. Now the scale begins to fold back toward us. The first things to disappear are individual galaxies. Clusters blur into concentrations along broad filaments. The filaments merge into a faint pattern extending through an observable region roughly 93 billion light-years across. At that scale, the Milky Way is invisible. So is the local group. So is the Sun. Earth leaves no measurable mark. Yet the map exists, because light from those distant regions reached instruments built on this planet. That is the quiet contradiction at the center of cosmic scale. We are small enough to vanish from the picture. We are capable of reconstructing the picture. The strongest supported answer to tonight's question is clear. The bright stellar disk of the Milky Way is roughly 100,000 light-years wide. The observable universe is about 930,000 times wider. Rounded gently, observable space is nearly 1 million Milky Way disks across. That answer carries an important limit. It applies to the observable universe. We do not know the total size of the whole cosmos. The horizon is the limit of information that has reached us, not a confirmed boundary where existence ends. Beyond it, space may continue through more galaxies, filaments, voids, and regions forever unavailable to our telescopes. The whole universe may be finite and vastly larger than what we see. It may possess a shape too broad for its curvature to appear within our horizon. It may also extend without end. Current evidence does not settle the question. Science becomes trustworthy when it separates measurement from possibility. The observable scale has been measured through light, redshift, geometry, and the history of expansion. The larger whole remains open. The uncertainty does not weaken the known comparison. It gives the comparison an honest boundary. Light needs roughly 100,000 years to cross the bright disk of the Milky Way. That one journey lasts far longer than recorded civilization. The local group extends across roughly 100 galactic widths. The cosmic web expands the count through hundreds, thousands, and tens of thousands. The observable diameter approaches 930,000. At every stage, the previous scale remains enormous. It simply stops being the largest thing in view. This may be the most useful way to approach cosmic size. A larger structure does not erase the smaller one. It contains it. The Milky Way remains vast even when placed inside observable space. Its size still determines travel times, communication delays, stellar histories, and the practical limits of anything living within it. Its hundreds of billions of stars do not become less real because other galaxies exist. Earth does not become less meaningful because it occupies little volume. Size tells us how much space something fills. It does not tell us how much value it can hold. The Milky Way is our galactic environment. Its earlier stars created many of the elements in our bodies. Its gravity shaped the orbit of the Sun. Its gas and dust supplied the material from which the solar system formed. Every ocean, forest, city, memory, and human life known to us exists inside one narrow region of this galaxy. The wider universe may contain an enormous population of other galaxies. Some may contain planets. Some may contain life. Some may contain observers asking their own version of the same question. We do not yet know. The Milky Way is the only galaxy humanity has experienced from within. It is the only one whose night sky became part of human culture before anyone understood what a galaxy was. For most of history, the pale band overhead seemed like a feature placed across the heavens. Now we know that it is an inside view of a structure 100,000 light-years wide. We know that the stars in that band are distant suns. We know the galaxy has spiral structure, a central bar, a supermassive black hole, a halo of ancient stars, satellite galaxies, hot gas, and an enormous dark matter environment. We know it grew through earlier mergers. We know its future relationship with Andromeda remains uncertain rather than inevitable. And we know that, despite its size and complexity, nearly 1 million bright Milky Way disks could be placed across observable space. Return to the pulse of light with which the journey began. It leaves one edge of the galaxy. It crosses sparse stellar neighborhoods, spiral structure, dust clouds, and the crowded central regions. While it travels, some stars are born, others die. Human civilization could appear and disappear many times before the pulse reaches the opposite side. 100,000 years pass. The light has crossed the Milky Way. On the scale of the observable universe, it has completed only about 1/930,000th of the full diameter. The great galactic crossing becomes one almost invisible step, And there may still be more universe beyond every horizon we can measure. We do not need to force that scale into perfect intuition tonight. The human mind evolved to understand nearby movement, familiar landscapes, faces, seasons, and paths that could be walked. It was not shaped to picture billions of light years directly. We approach those distances through layers. A signal crossing the moon's orbit, sunlight traveling 8 minutes, a nearby star 4 years away, a galactic disk crossed in 100,000 years, a neighbouring spiral reached after 2.5 million, a cosmic horizon measured in tens of billions. Each layer gives the next one a foundation. The universe remains too large to hold as one complete mental image, but it becomes clear enough to approach. The Milky Way is immense. The observable universe is nearly 1 million times wider. The full universe remains unknown. And here, inside one galaxy, beside one ordinary star, a small world has learned enough to measure the darkness around it. Good night.